Hey everybody, hope you had a nice quick break. Let's pop in directly to the question everybody's asking. What is deep learning? Right? You've heard the name, you've heard the buzz. It's everything. Well, I'm going to give you a very short history and an idea of what machine learning is and isn't. Okay? So there have been over 60 years, no, we're on 70 years now, over 70 years of people using mathematics to describe how neurons work and trying to use those to understand how learning can take place. All right? Well, to do that, let's start at the very, very beginning. What actually is a neuron? So neurons are electrochemical cells, right? They move ions of chemicals in and out of the cell, and by doing that, they create an electric charge. And that electric charge can move along a cell, right? So we can, if the cell has an action potential, a little electrical spike, it will travel along the axon, which is the output of a neuron. And when it gets down to the edge of a neuron down here, the electrical potential is going to open up the cell and let it drop little bits of chemical out, and those bits of chemical are going to attach to the next cell, and that is going to cause that cell's membrane to start throwing ions in and out, which will create another electrical potential, and maybe that signal will propagate along to the next cell along. Or maybe it won't. Maybe at this stage everything breaks down and no signal goes forward. This is the nature of neurons. They're fairly noisy in terms of individual actions. They also are reactive to a lot of things. Okay, so what we talk about as an electrical impulse is not the only thing going on. These are living in baths of chemicals, and those baths of chemicals are changing the way in which the neuron acts all the time. Most neurons don't act like light switches. They're not on or off. They have varying levels of either readiness to fire or not, and they can fire their action potentials at many different kinds of patterns of firing. The details of it are much too hard to get into in even a single quarter all the way through, so just trust me that they're very interesting and dynamic things. Now, how do we make that into math, right? Because people have always gone after understanding the brain because we know the brain, or at least the human brain, does some pretty amazing things. So if we want to understand intelligence and amazing things, how can we build stuff like the brain? Well, a long time ago, McCulloch and Pitts created this kind of idea that neurons could be seen like little elements of electric circuit. Okay, literally like electric circuit, like light switches flipping on and off. Like I just said, neurons don't act, right? But this was the 40s. They didn't really understand everything, and this was a great simplification of what little we knew at the time, and in a way to kind of understand how the brain might operate. Okay? So the idea fundamentally is, if you looked at that picture that I had a second ago of a neuron, here are these little units, and maybe you have, signal arriving here and here, and depending upon if you have lots of signal, then maybe you get an action potential out that way, and if you don't, if you have much less, then maybe there's nothing here. Maybe there's great huge silence. Okay? And the mathematical formulation of all this is that we're going to integrate all the things coming in. We're going to sum them up, and we're either going to fire or not fire according to some sort of threshold. Magic has a lot to say. I'm sure you can hear him. Do you want to say hi? Come on up. Somebody is bored. You were just napping on the couch. Yes. All right, Magic, I have to finish. Off you go. All right, Magic's telling me McCulloch Pitts is lame. So just FYI, you can come up with ways in which inputs like can operate in logic gate fashion. Okay, this is the way that computer chips operate. All right, so if we have a 1 and a 1 and we add it up, we get a 2. And if we set our firing threshold at 1.5, anything over 1.5 is going to fire us, so 2 is going to fire us. We've implemented a logical AND. And you can set up logical ORs and logical NOTs and stuff like that. And, FYI, if you go through a little bit of computer science, you'll find out that if you can implement an AND and a NOT, then you have a universal Turing complete kind of machine which can do any kind of computation. All right, so it seems exciting, right? These kinds of neurons as logic gates may mean that the brain computes that way. So history, right? In the 50s, this guy named Frank Rosenblatt came up with a perceptron, right? The perceptron that Rosenblatt came up with is rather like McCulloch-Pitts neurons, except it learns how to set those thresholds and those weights instead of somebody writing them down. All right? And as you can see from this article, feel free to pause and read if you're interested. This is a massive hype train, okay? Like Rosenblatt had already invented the startup company Overclaim back in the 50s. And you see all kinds of awesome things here, so it's possible that they will become conscious, just like us. Spoiler alert, didn't happen. So, this is like the first case of somebody claiming AI and getting loads of dollars for it that I'm aware of. So, at any rate, when you want to see what Frank's perceptron looked like, there were an awful lot of wires involved. Nowadays, even back in the 80s and 90s, you could implement a perceptron on something that would fit in a digital calculator or something like that, right? Of course, your computer is way better than that. All right, so that hype train that Frank Rosenblatt started caused some havoc, right? That, along with some other failures of massively hyped AI systems involved in machine translation, created the first what's called AI winter. And, dollars had been going up for funding, and then they just went, right? And then some new events in the 80s where we understood for the first time that why some of the failures happened here. The neural networks that were coming out basically got shut down by this famous book by Minsky and Papert, which showed their limitations at the time. And then here in the 80s and 90s, we started to get some new stuff happening. This was Lisp machines, and then a crash, and then a new takeoff of neural networks here in the 90s. And it's been growing ever since, and lots of dollars and work involved. Magic? Yes. Yeah, I'm ignoring you. All right. So what happened after the perceptron died? Well, it didn't really die so much as it got bigger, okay? A perceptron is a single neuron taking a bunch of inputs, okay? So this is a single perceptron. And Frank Rosenblatt himself started doing this kind of stuff where he'd have multiple perceptrons all arranged in a row, and they would all take the same inputs, but maybe one would process stuff over here on the left side, and another one would process stuff over on the right, and things like that. So the big innovation of the 90s was to figure out that you can stack them in multiple layers. So perceptron on perceptron on perceptron. Okay? Magic, do you want to come up again? little jerk. Okay, so how does this work, right? With a perceptron, you could just train the perceptron to get the right outputs. Well, how do we do it with this is what's called a multi-layer perceptron. Well, we give it an input. I was hoping that would make him jealous. The input produces a lot of electrical signals that go forward. Okay, and this causes that, causes that, causes that, and leads out to some output. Okay, and the label comes out of our system. It says this is a healthcare worker. And you tell the multi-layer perceptron, no, bad perceptron, right? What we have here is a cat, not a healthcare worker. So this produces an error signal which goes backwards through these neural networks and tries to change the connections between the neurons to make it produce the desired output cat. All right? So that's the method. Now, does this actually work like a brain? The answer, I think you can pretty much guess, is no. Right? This is what actual brain networks look like, traced by microscopy. They don't bear any real resemblance to this kind of thing with its organized single sets of neurons that go from here to there in a logical forward progression, right? The connectivity in this land is all kinds of wiggly, right? The connectivity goes around and around and around. It goes back on itself. It goes in big jumps forward and in big jumps back. Okay. The dynamics are not just signals moving along. There's things that change over hours or days as chemicals change in the brain. All right. So we're going to take a 1-second pause while I kick the cat out of the office. Come on, cat. See, that's the magic of biological learning right there. He's got me perfectly trained. Try that with an artificial neural network. All right, so what is this deep learning stuff? How is it different than what we just saw? Well, that multi-layer perceptron I showed you had, what, like 3 hidden layers? This is ResNet 50. The 50 number is the number of layers it has. So this is why we call this deep learning, okay? So it's the same deal, right? We have over here inputs. I'm going to draw my cat over here. So here's my cat image coming in. You can tell what a great artist I am. All right, so there's our input layer. We turn pictures into electrical activity that go through processing elements, and they go deet, 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 and they make jumps, and they, et cetera, et cetera. And on the output, we have that label, which says, oh, and I drew it behind my own head. So, all right. So 50 layers instead of 3. This is deep, man, really, really deep. Okay. Not only does it have 50 layers, it has something like 20 million-ish parameters that have to be set. And that's what learning is setting those numbers to get the best possible outcome. All right. So, and since 2016, there are variants of ResNet that go over 1,000 layers deep. Okay? And there are other architectures which are not quite as deep as ResNet, but they have just insane numbers of parameters, like 175 billion for the brand new GPT-3. Okay? For your information, when you're wondering how you build 175 billion parameter neural network, The answer is you basically have to be a internet company sized endeavor and use a lot of servers for months at a time to train something like that. There are estimates that training something like GPT-3 might might cause more energy than many cars over their entire lifetimes. Okay, just the electricity to train it. All right. But what can something like GPT-3 do? Well, let's see if I can. Well, I'm going to have to use a little ingenuity because the iPad's not controlling this. So we can do things like GPT-3 is a language processing deep learning network. And it turns out that GPT-3 can do some amazing things, like be trained to generate regular expressions. Regular expressions, if you haven't had the pleasure yet, are something you will learn to use a lot in computer programming for finding stuff in a set of strings, right? So you have a massive amount of text and you want to find the right kind of thing, like the place where the web scraping should begin, right? So you're going to use a regular expression. So you can easily train GPT-3 to do regular expressions. You can train it to create neural networks, right? It's a neural network. You can train it to create neural networks. You can train it to give a text description of a desired face, and it will automatically generate a face. Not find a face on the internet. It will create a face from trained data. So these are not people, these are made up images. Okay? So it can write your software for you. It can do all kinds of things. All right. Seems really, really impressive, right? Of course, for every demo like this, there's probably 5 things that they tried to make it do that it couldn't do. Okay, so it's not some sort of magic general intelligence. Right. So what makes a deep learning network different than an artificial neural network? Okay, it's not just that it's deep, right? There's something else. That's basically nothing to do with neural networks. Okay, the differences between a deep learning network and what was going on in the 1990s is really just tricks, right? So, like I said, since 1990, we've known that artificial neural networks, like a multi-layer perceptron with just a single hidden layer in the middle, are universal function approximators. So they can solve any old task you want. Okay? So what's happened is that what we've arrived at is internet-sized data sets. So we have so much data to train that we didn't have in 1990. We have the computing power to train things that we didn't have in 1990. So those are really what enabled deep learning, because there was nothing there was no problem set to artificial neural networks in 1990 that you really needed 50 layers for. Okay? The other kind of cool stuff is that we have these trick architectures and trick methods of teaching the neural network. Okay, what do I mean by that? So here's a trick way of training your network. If your network is supposed to be learning natural language, like this guy whose name is Bert, like as in the Sesame Street character, but of course Bert is an acronym because all algorithms have stupid acronyms, right? And it's trying to learn about English. Well, what do? You feed it all the English on Wikipedia, okay? And how does it train itself, right? We don't want people to have to sit down and label all of Wikipedia in some supervised way for the network to learn about. That's impossible, okay? We can't have that. Instead, what BERT does is it masks out a random 15% of words. Okay? So it loads up a Wikipedia article and it closes its eyes over 15% of the words. So it leaves, 85% of the words intact, but it just kind of censor bars out the other 15%. And then what BERT tries to do is it tries to teach itself to predict the missing 15%. Okay? So this is like just a clever trick where what BERT learns to do is to make not a supervised learning system, but it's self-supervised. It takes complete data, Wikipedia articles, it removes part of them, it learns to predict the things that it removed, and it has the right answers because it removed them, so it knows how to supervise itself and create the right answer. This is another example, which is trying to make something that can do that super resolution enhance thing that you'll see when, the spies have like a really grainy video camera image and somehow they blow it up 30 times so they can see what the license plate is. So you can do that same trick. You can start with a high resolution image, and because it's high resolution, you can make a crap version of that image, and you can give that crap version of the image to a network and try to train it with the correct high resolution image, which then enables you to take lower resolution inputs and create super resolution outputs. Okay? So what can't deep learning do? Okay, it needs an incredible amount of data. So if you don't have a lot of data, it may not be the right thing. Okay? It also may take days and days to train, depending upon what the network is that you're trying to do and what the task and what the inputs are. It's also really hard to know why deep learning does something. It's not interpretable. Something like a regression or a decision tree, like we already looked at, that's interpretable. Okay? So it can learn things you don't want it to, is another interesting thing. So there was a deep learning network that was trying to learn to predict the severity of somebody's COVID case from chest x-rays. Okay, so they wanted to see, could we take a chest x-ray and predict whether somebody's going to end up in the ICU or not. Okay, what happened is it got really, really good performance. It was like, yes, we can predict the people that are going to get really sick. The problem is training data. The training data that it was given was data from really sick people and not so sick people. The not so sick people were taken to the regular x-ray machine. The really, really sick people, they had to bring the x-ray machine to the bedside of the person who was in the intensive care unit. It's a different x-ray machine than the one that people were visiting, down in the basement. So this means that there were unique features because of the machine on the x-ray that had nothing to do with the medical changes of the person, right? It was like little registration marks on the x-ray image. And it picked up on that, and it learned that if somebody has those kinds of marks, on their image, it's a portable x-ray machine, and that means you're probably going to die. So clearly that's an example of overfitting. And deep learning being a super powerful learning algorithm, even more powerful than a decision tree, right? It can overfit unique features of the data and not find the big patterns we want, but just fit the noise. Okay, lastly, I just want to say that deep learning doesn't learn. You can't train it on one thing and have it do something completely different. Okay, this is an engineering system. You build it to do one or two related things. You can't build it to learn to classify cats and suddenly it can make you breakfast. Okay, it's not a general intelligence system. All right, so when would you use it? You could use it when you have tons and tons of data. That's a good time. You would also want to use it when you have a difficult time coming up with the right features to solve the task by a simpler statistical method or lesser machine learning method. Okay? So there are some deep learning systems that have a two-step where there's like a big build that takes a lot of energy and time to train it, and then there's like little fine tunings you can do to hijack it and use it for a particular task. So if there is a pre-existing network that can be fine-tuned for your task, that might be a good use case for deep learning. Okay, if somebody else has already done the hard work and made the big network, you just have to take it and twiddle it for a couple of hours on new data. Okay? And always, 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 I think if you don't know what you're doing with deep learning, leave it alone. It's a pretty kind of complicated art more than it's a science. Okay, so that's all I had for you right now, and we'll chat again soon. Hasta.